Okay, so let's imagine that we have an object that is just sitting there, um, maybe in two-dimensional space. So it's an object of mass m. Let's just put some numbers. Let's say it's 1 kilogram. And we're going to introduce Newton's laws. So we're going to start with Newton's second law, which is a relationship between acceleration and force. And the origin of this law is, to some degree, just a guess. So the law says that mass times acceleration is equal to the sum of the forces acting on this object. So this is supposed to be an I. So here are the forces. We sum over all of these forces. Or we can just write this as, here's a net force acting on the object F. That's the net force, where F is the sum of all the forces acting on the object. Okay, so this is going to allow us to get the acceleration, and then we'll be where we were previously, where we can use kinematic equations to completely describe the behavior of the object. But now we've introduced this new property of an object, its mass. And in some sense, it's a quantity, it's an ability to resist being accelerated, because when I solve for the acceleration, then I have to divide by this property, the mass. For a given force, the greater the mass is, the smaller the acceleration. So in some sense, this is resistance to being accelerated. So let's do an example. Let's imagine that we have this object here of 1 kilogram, and we have a force acting on it. So it's just sitting there at rest, it's not moving. And we act on it with a force which is, let's say we're in the XY plane. So we're going to act on it with that force in newtons. So we're going to use units of newtons, in this case for force. And we want to describe the motion of this object. So in other words, let's find its acceleration, its velocity, and its position at all times. So we have the force at all times. It's a constant force. What happens to the acceleration? Well, by Newton's second law, we have to do that. And that's just 2I hat minus 3J hat newtons over the mass, which is 1 kilogram in this case. And so we get an acceleration that numerically looks exactly the same, because I chose 1 for the value of the mass. But this, of course, is newtons per kilogram, or meters per second squared. So now I want the velocity. So I'm going to integrate the acceleration. I'm now in familiar territory. I integrate the 2 here in time, so I get 2t, and then I have to add a constant of integration, but we start at rest, so there is no x, there is no v naught x, so I just have an I hat there. Same thing is true for the y component, or j component. I get a 3t plus the v naught y, but that's 0 because the object starts at rest, and so I just have a j hat. That's the velocity vector as a function of time. And of course, this is meters per second. And then I can get the position in this two-dimensional space by integrating that and adding the initial position, which if we decide that this is the origin, then I integrate this, I get t squared over 2. That cancels the 2. I get t squared I hat minus 3t squared over 2 j hat. And that's in meters, and so I have the position vector as a function of time. It's not surprising that it's a quadratic equation. Linear in time here, quadratic in time here, and constant for the acceleration.